Hi everyone, welcome to the CSP seminar this week. So this week is our great pleasure to have Professor Richard Zhang from UIUC ECE department to give us a talk. Professor Richard Zhang received his PhD from MIT and he did a postdoc with Javad Lavie at UC Berkeley. And his research interest is at the intersection of optimization, machine learning, and application in power and energy systems. So today, I think he will give us a talk that many of us will be very interested in. It's on overparameterization and global probability in non-convex low-rank matrix estimation and optimization problems. With that, the room is yours.
Great. Thank you very much for the introduction. I'm very glad to be here. Thank you for the invitation. So let's begin by talking about exactly what we mean when we say low-rank matrix estimation and optimization. So when we talk about low-rank matrix estimation, it appears widely in communication signal processing. That's why we care about this problem so much, in which we're trying to find here an n by n matrix that doesn't need to be square. It's low rank. Perhaps we have linear measurements. Perhaps we have nonlinear measurements, but the key challenge here is that this constraint that this matrix should be rank constraint is low rank, that this is non-convex. As we know from the late 2000s and the early 2010s that it turned out this problem, you could solve it using this heuristic in which you have a convex penalty, right? This trace, this nuclear norm penalty in which you solve this, and you're able to recover a estimation by penalizing this maximum likelihood least squares loss. And in fact, some later work then actually showed that this is minimax optimal in the sense that this is the best possible estimation that you can get under this noise model, etc. So this is all classical stuff, and even more that you can efficiently solve this convex but non-smooth problem with this nuclear norm constraint. You can actually solve this as a smooth convex optimization over an n by 2n matrix. Now it's just a slightly bigger version of this least squares objective with a trace which is linear, subject to the semi-definite constraint. This should be easy because this is semi-definite programming, and this is very old at this point, polynomial time solvable. And then when we show this to practitioners and practitioners try to apply this to their real world data, they discover that, okay, well, actually, there's a catch. A semi-definite program takes at least cubic time and quadratic memory to solve. And so they find they can't actually solve any of these problems in real life. Your data sets routinely have your n by n matrix, but your n is 1,000,000, so you can't solve it. So what's really the problem here is this optimization, this low-rank matrix optimization. Let's just simplify our discussion. Of course, we can talk about more complicated problems, but there's a very simple case, which is true here. And you have an objective that is just a convex C2, this twice differentiable, continuously differentiable function, and you're trying to minimize it over a semi-definite matrix that's n by n. And really the trouble here seems very trivial. It's just that the matrix is n by n, therefore it has n squared elements. But as I said, for practitioners, it's a huge problem because n is very large and n squared is ginormous, and we can never hope to solve this problem. And we asked, is there a way to try to solve this problem by exploiting structure? So this problem arising in statistical estimation has a very important structure, the one that we just talked about, that we're trying to estimate a low-rank matrix as the outcome of the solution. So when we solve this, we'll expect that the semi-definite program, once you solve it, the solution is going to be low rank. You design this problem this way, right? You have this nuclear norm constraint SDP so that when you solve it, it's going to be low rank. And this low rankness, we ask, can we exploit this assumption, the structure as a formal assumption? And this is very popular to try to come here and say, well, one thing we can do is we know that the solution is going to be low rank, then we can try to optimize over a low rank matrix directly by factoring it. So here what we're doing is we're introducing this n by r matrix U, and we pick this r to be bigger than r star here so that these two problems are going to be the same. And the important thing here is that we're picking an n by r, but this is low rank, and so this r can be very small, and potentially if r is small enough, then it's still optimizing over n by n matrix with n squared elements. You're just optimizing over n elements, and so this problem on the right you can actually solve, whereas the problem on the left you cannot hope to solve. So of course you pay something, and the the trouble is by doing this factorization, expressing this semi-definite matrix M as the outer product of this smaller matrix, this rectangular, this tall and skinny rectangular matrix, you've made the objective now non-convex. But nevertheless, you can try and solve this using gradient descent or whatever algorithm that you like. And back in 2003 and 2005, Urbana-Champaign did this, and they reported in these two papers that so local optimization seems to solve this non-convex problem anyway. So at the time, some people in semi-definite programming picked up this result. At this point, because of the machine learning community and some of this low-rank models showing up, this has become very widespread. And at this point, it's our impression is that any semi-definite program, you can just go in there, you can factor it. And the important thing is that this, in general, this rank constraint should be NP hard, but I mean, we're picking the rank to be greater than R star, the relaxation. It's not an NP hard problem because you can just solve the convex problem to get the solution to this non-convex problem. It's not NP hard. Urbana-Champaign should always work. So who cares if Urbana-Champaign works or not? I want to give you a real world motivation. Okay, so in electric power systems, this problem shows up, and you're trying to estimate a low-rank matrix. It doesn't start off as a low-rank matrix. What you're trying to do is you're trying to estimate the voltages in the power system. Okay, technically, it's the voltage phases. You have a bunch of AC voltages, and you're trying to measure the magnitude and the phases. And the phases you can't directly measure, but you can measure power flowing between nodes. One node being Ann Arbor, another node being Detroit, for example. You can measure the power going between Ann Arbor and Detroit, and you can't measure the phase difference because it's 40 minutes drive, but you can measure the power and try to infer the phase difference. And of course, this is actually a fishless structure here because you have current times voltage and current is linear with respect to voltage. So you can believe me when I say I can come up with a phi that is a quadratic, and if I solve it, then I'm going to get a solution to this problem. And now the important thing here is getting a solution to this problem means keeping the lights on. And when you solve this problem incorrectly and you make a mistake in 2003, there was in fact a blackout that knocked out, including Ann Arbor, right, knocked out broadly the Northeast United States. Almost 100 people died from this. Okay, it's very, very serious. So you can imagine you solve this problem wrong, you don't get global optimality, you could have trouble. So when you look at it from the perspective that we just described as a low-rank matrix optimization, what you discover is, okay, it's a semi-definite program. It's a quadratic objective, the semi-definite constraint. And actually, you just solve it, you get a rank 1 solution. That's a globally optimal solution. So it's a very, very easy problem from our perspective. But of course, this is n by n, and n is very large. And because n is very large, you cannot solve the semi-definite program. So instead, people go in here and they solve the Urbana-Champaign. They don't realize they're doing it, but this is what they're doing. They're doing the Urbana-Champaign, okay? And they do it because it's super fast, and super fast you can actually solve it. And they believe it always worked. We went here, and very quickly, we found counterexamples. So we found instances whose loss looked something like this, okay? So you can see, you see a local min. And when you run an algorithm on this counterexample, what you see is, okay, the algorithm might not even converge. It might just go some random place. It might converge, but converge to a spurious local min, a local min that has nothing to do with how the power system is actually behaving at this moment. Or it can converge to the true global min, okay? And if you talk to power systems researchers, they say, well, okay, clearly it's very important for you to pick the initial point correctly, right? Or else you might get stuck. But I mean, that's a little bit unsatisfactory. Okay, if your system is safe, then maybe you start your local search with a safe initial point. But if your system is not safe, you start with a safe initial point, but your system is actually not, that's not good, right? So it's not clear how you can reliably always get the correct estimation because neither one, you don't really know which one's correct, right? The second point here is you actually don't know which one's correct. Now, you'll tell me, well, one thing we can do is we're trying to minimize the loss function. So we can just evaluate the value of the loss function. And then you can come in here and you can see that, okay, well, the failure to converge, the loss function is 0.9, right? But the spurious local min had loss function 0.1, and the global min has loss 0. how do you tell the global min and the local min apart? So how do you verify by conversion one of these that is actually the correct estimation? So lots of questions, right? So you have this approach that people have tackled it using this non-convex way that's scalable, but you're opening up this kind of ones where it might fail to converge to the global min, it might converge to a spurious local min. And when it even converges to the global min, you're not too sure. You're worried that it might converge to the spurious local min. So the point of today's talk is to convince you that overparameterization for this particular problem here might offer a solution. Okay, so what do I mean by overparameterization? I mean something very, very simple. So this thing here, in the previous instance, my left-hand side, the solution is rank 1. So my right-hand side, I can solve it with rank 1, and the globally optimal point is going to solve the left-hand side. But I purposely keep increasing the rank. So I increase it to rank 2, rank 3, rank 4. I just keep increasing the rank. And I claim if I keep doing that, I'm going to get certified global optimality. And not just global optimality, but actually certified. What does that mean? Certified. You're non-convex. So convex is certified because the gradient is equal to 0 and it's convex. What do you mean by non-convex is certified? So we're going to talk about that, okay? So the first question that I'm going to answer is, wait, how is it even possible? So what I'm claiming is as you increase the rank, that this non-convex problem become more and more convex-like. And this is consistent with experience that it loses some of these bad local min until eventually it has no more local min and you succeed. Okay, so that's the first claim that I'm making. The second is actually you can achieve certified global optimality. So you can achieve global optimality and you can certify it afterwards. And you can do this efficiently. And using algorithms very similar to gradient descent, you can actually achieve this. And finally, we're going to see that this technique is actually going to be applicable to real-world data sets. And we're going to see some examples on medical imaging and on neural network adversarial machine learning certification. Okay, so let's begin with the first point here. Okay, so how does overparameterization actually eliminate local min? So even though this is rank 1, I purposely increase the rank, and by rank 2, it gets a little bit more convex-like, a little bit more until it doesn't become convex. The problem on the right will never be convex. Yeah, it will never be convex even if it had no local min. So what we need to do is we need a new notion of something that's kind of like a convex problem, but it's not convex, but doesn't have local min. So what you need is this notion that is not convex, but doesn't have a local min, so that every second order point, so a point that has no gradient, and the curvature around it is locally spherical. So what does that mean? It means around every point, it either has a large gradient, and you can use gradient descent, and you can make progress, or that it's the gradient at this point is equal to 0, but around that point there's some negative curvature, and compute the Hessian of the function. I can escape there. And if the Hessian is also positive semi-definite, then it's guaranteed to be globally optimal. Okay, so that's what I mean. A function that satisfies this might not be convex. Obviously, convex trivially satisfies this, but a non-convex function that satisfies this is convex-like insofar as you can solve it to global optimality. Okay, so the first kind of guarantees that existed, that our first inclination that was even possible was in the machine learning community when it was kind of discovered that you can use the condition number of this function phi, this convex function, right? So we turn the convex function to non-convex function f, but this convex function phi has a condition number that's just the gradient Lipschitz constant and the strong convexity the strong convexity parameter, which you can also view this as just the largest eigenvalue and the smallest eigenvalue of the Hessian. Right? So that ratio is a condition number, and it turns out that when you apply this to statistical learning problems and you have a diversity of measurements, that this condition number turns out to be finite. Okay, under some rank constraint, let's ignore that to make this conversation a little bit easier. So you have this scale, and this condition number can go from 1 to some value. And in practice, you find in the real world that your condition number is just some finite value. And what this community showed is that if your condition number is small enough, right? So less than 1.5, then they guarantee this property. So it's not convex. I'm not claiming it's convex, but if you find me a point that has no gradient and positive curvature, then it's globally optimal. Okay, so obviously that's very exciting, and perhaps for our problem, we can push this all the way up to our our actual value in the real world. I go to my power systems, I figure out what the condition number is. If I can just improve this result enough, I come up to here, then I'm done. But then when we're trying to do this, what we discovered is actually it's false, because you can come up with counterexamples. Okay, so you can come up with a counterexample with condition number greater than or equal to 3. So that means, yeah, so if you're almost perfectly conditioned, if your condition number is like 1.2, then I guarantee you that every local min is a global min. But if your condition number is greater than or equal to 3, then I'm not saying this is the case for your problem. I'm saying you can't make a guarantee because I can give you a counterexample, right? So empirically, maybe or maybe not, you don't have any local min, but I tell you can't make a guarantee because I can give you a counterexample in the worst case that the condition number is pretty close to 1, right? So you need it to almost be perfectly to 1 for this to be a guarantee. So, okay, so this seems to be a very, very limited property that, okay, holds true in some cases, but in general is very unlikely to happen. And then so this idea that maybe increasing the rank is a very important property, it actually came from a different group of researchers who are looking at these synchronization problems, phase synchronization problems. And here, let's just remind ourselves what this R star is here, right? That is the relaxation rank of the convex problem. So for the power system one, it was equal to 1. If you can solve this, you get a rank 1 solution, solves our problem, right? So this R star here is it's the underlying true rank, and we're trying to increase the search rank to perhaps make it more convex. Okay, so your search rank, it can't be less than R star, because if it's less than R star, then you can't even solve the convex problem. It's not actually polynomial time solvable. It's actually NP hard. Okay, so you can't actually set the rank to be less than R star, but the hope is that you go a little bit above, and maybe it becomes convex. And what they were able to show in this community, and in the real world, it seems like once you increase the rank enough, it starts working. Okay, so this is why they went embarked on this research. And what they were able to show in this community is if you increase that search rank all the way up, okay, all the way up to n, then I can guarantee that it has no local min. Okay, so if you overparameterize, you increase the rank. So even though it's got a rank 1 solution, I purposely search for a higher rank. And if I search for rank n, then it's but obviously, anyone who solved this problem will tell you, okay, but n squared variables. Like the whole point was to avoid, right? You said this problem here had n squared variables and you can't solve it. If you force me to solve this problem here with n squared variables, why do I need this non-convex approach in the first place? So this basically has no practical value at all. It's a purely theoretical result, right? What we want is something that's like 5. We don't want n. N's 100 million. We want 5. And so there was a lot of work trying to understand, can we prove overparameterization with rank is equal to 5? And there's a lot of work in machine learning in general that said overparameterization is the key for why non-convex problems act like convex. So there was a lot of belief that we could prove that with a search rank of 5, it would start to work. Okay, but what they found was more counterexamples, unfortunately. What they found was that actually for this setup, you can find a phi such that, okay, that up to omega n, that you're going to get stuck. I can find you a counterexample, I can give you a starting point for which is not the global min, and you're going to get stuck. So that means it doesn't mean that your problem will fail, right? Your problem probably with a search rank of 5, you'll succeed. But this counterexample says, once again, you can't prove it because I can give you a counterexample that falsifies this belief, okay? So what do we have here? We have a bunch of negative results, right? So at this point, most people believe that this is just an empirical fact that can never be proved. It has no bearing on theory, and this is just in practice, you have a terrible condition number, but you solve this non-convex problem, it succeeds anyway. And if it doesn't succeed, we increase the rank from R star is equal to 1 or 2 to 5 and it succeeds. Okay, but you can't prove it, and it is what it is. Okay, and maybe empirical success in both cases just can never be rigorously guaranteed in that set because there's a fundamental gap between theory and practice. So when I came to this problem, what I said was, hold on, you guys are missing something here, okay? So you have these guarantees based on condition number, and you have these guarantees based on a search rank and this overparameterization, but they don't talk to each other, okay? So this condition number guarantee, okay, what rank does it apply to? Well, it applies to any rank. It does not consider overparameterization at all, all right? And conversely, now you look at the overparameterization guarantee, okay? It actually works for all condition numbers. It works for all condition numbers. So it's very intuitive for you to ask, is it really the case that for problems that are well-conditioned, that you still get stuck, right? So is it the case that, like, for example, if I take a well-conditioned case and I force it to overparameterize, right? Maybe then I can tolerate a better condition number. Or put it another way, right? If my condition number is here, right? And this blue line here, and I can't make a guarantee. And here with overparameterizes n, I don't want n, but I can make a guarantee. Maybe I can increase that rank from R star to 20. And I see that the green part goes over, right? Because the counterexamples are ill-conditioned, right? So can I mix these two ideas up, right? And such that, right, if my rank is much larger than R star, but less than n, can I make a better guarantee for a specific condition number? And so that's really the idea, right? But it's still the question is how much rank do you need? How much rank do you need? Because if you go through this procedure and you need R is greater than n divided by 2, then that's still n by n, right? N divided by 2, that's still not good. What you want to show is that if my condition number is good and I'm somewhere along this line, then with a rank that's ideally order 1, then you can guarantee success. And so what really the main result here is the following statement, right? So what we're saying is that if your function is well conditioned, then overparameterization is going to make it global. It's going to eliminate spurious local minimum. Okay, so what we're trying to say is that I have this search rank here, okay, and I have to increase my search rank above R star, right? What we claim here is that, okay, so actually the negative result here, it claims that R star plus some constant, you still can't make any guarantees, but there exists some constant, and that constant is actually what? This constant is actually determined by the condition number here, okay? So this plus is constant, then you're guaranteed to succeed. So this constant times R star versus the constant, this is the gap between the necessity and the sufficiency. What we're saying is that if your condition number is not infinite, then with the order 1 overparameterization, you can guarantee that there's no local min. Okay, so this working actually relies on you both having overparameterization and well conditioning simultaneously. If you only have one, or if you only have the other, then the C will either be infinity, it's not going to work, right? So there's the first overparameterization guarantee to actually allow you to have a search rank that's, let's say 5, right? It's not equal to 1, but 5 is pretty good, okay? But it does require you to have a finite condition, right? If you have an infinite condition, this is actually false. On the other hand, it does also allow you to tolerate any condition number and make a guarantee, okay? So how do we prove such a statement? How do we prove such a statement? Well, what is the key intuition behind to be able to prove a result like this? Well, really what we're doing is we're talking about counterexamples. We're looking for counterexamples. So for overparameterization, we still look for counterexamples. So kind of a general statement is if I can come in here, right, I make the claim. So if you overparameterize a little bit, then you don't have any local min, right? And you don't like me and you want to disprove my paper, right? Then what you can try and do is you can try to look for a counterexample. What does a counterexample actually look like concretely here? What you want to find is you want to find a phi, right? You want to find a phi that has a global min, right? Has a global m star for which the rank is r star. Okay, and I want to find this phi such that when I turn it into a non-convex function, this f here, okay, that it has this point x that is a first order point, its gradient is equal to 0. It's a second order point, its curvature is positive, but it is not the global min. Yeah, so that's a counterexample. And if you find a counterexample that also has this overparameterization, then you falsify my statement, and I have to withdraw my claim, right? But so if there exists, then my claim is false, right? But my hope is that if you can't find a counterexample, if you can't find one, then you have to accept my claim is true. Okay, so that's the basic argument for being able to prove something like this. So look for a counterexample, and if you can't find one, then you have to accept my statement is true. Okay, so this statement here, right, that we hope the community in general hope that overparameterization would be enough is false. Okay, so counterexamples always exist. In fact, a counterexample exists for every value of r less than n. So r is equal to n minus 1. I can find you a counterexample in which you hoped that overparameterization would eliminate local min, but it has a local min. Okay, so that's very disappointing. But the key thing is to realize that all of these counterexamples are going to be ill-conditioned. Okay, so if I control the conditioning, then I can eliminate those counterexamples. So that's the key idea. So let me draw you a picture here, right? So if the condition number is close to 1, if the condition number is close to 1, then you can't have any counterexamples. We already know that you can't. Every local min is global min. This we already know, right? And simultaneously, we know that there exist cases in which they're counterexamples. What we're arguing is that their condition number must be bad. They must be bad. So if I control the overparameterization ratio and I keep looking, right, and the condition number is high, and I kind of exhaust all the possible ways in which I can have a global min, I can have some engineered local min, right, bad local min, a second order point, I can exhaust all of them, then I'm going to reach a threshold. And I'm hoping that this threshold here is going to be a function of how much I overparameterize. And if I can find that this threshold, it goes up as I overparameterize, then that shows me that indeed I can actually control the existence of spurious loci. Okay, so more rigorously, what we're really trying to say is, so if the condition number is less than equal to this function of the overparameterization ratio, then there's no bad local min. Okay, so basically, if you give me any function with a condition number, I can find an overparameterization ratio to exceed it. So if this is 5, then I know that if I pick this equal to 2, pick it to 3, then there'll be no local min. So that's now the claim. Okay, and then so how do we prove it? Well, how we disprove it is we try to find the best condition counterexample. So if I find a best condition counterexample with the smallest condition number, that's a counterexample, right, for a bad point x and a minimizer x, a ZZ transpose. Well, find the best condition counterexample over all choices of x and z, right? And it falsifies this statement by being lower than this threshold, then the statement is false, right? So if I find a counterexample, the best condition counterexample, and it's lower than this value, then the statement is false because it's a counterexample. And if I solve this optimization problem, this complicated optimization problem, and its minimum is actually greater or equal to this threshold, then the claim is true. So that's the idea of the proof, okay? And now actually trying to solve this optimization problem to get this threshold turns out to be most of the difficulty of this proof. It turns out that the first part, the finding a counterexample for a fixed engineer point x and global min z, turns out to, okay, it's not quite a convex SDP, but it can be lower bounded by a convex SDP, okay? So then this we can solve. Can we solve in closed form? We can sort of solve in closed form, and then we try to optimize this seamless for program over all pairs of engineer points x and global min z, okay? And so the idea is for each pair of x and z, we solve the SDP and then we optimize it over all pairs. Okay, so and then we're going to find that the threshold is 1 plus 2 square root of r divided by r star, and then so the claim is true. So the major difficulty one is that, I mean, you want to solve this so you can optimize it over all pairs, but okay, you can't really solve in closed form. And the second difficulty is if you try to lower bound the SDP, then the lower bound might be too loose and you can't prove this statement. And the third difficulty, and this is really a big one, is even pretending that you can solve this thing here, you still have to optimize over all n r plus r star elements in these two possible matrices, and you have to do it on paper to actually prove a theorem. So, okay, so these very major difficulties, how do you overcome these? The first key step is that I prove this lemma here, that is a closed form solution, so lower bound, and I numerically verified it would be tight enough to prove our desired claim. And the second thing, as it turned out, is a very kind of subtle thing, but I use this tool from integer programming, something called a valid inequality or a cutting plane. It turns out that this non-convex optimization problem, you can introduce a cutting plane, it'll cut right at the global min. Now, why does it cut at the global min? I'm not 100% sure, but you can prove this claim, and once you prove this claim, okay, you have these two things, and you have this lower bound that's a function of just this gamma as a function of alpha and beta, as alpha and beta are functions of x and z, right? But this alpha and beta are constrained by this. You just go in here, you optimize this gamma here over this constraint alpha and beta, and you get your claim, and you prove yes.
I was expecting phi, the function, to be somewhere in here. Could you?
So what we're doing, yeah. So what we're doing is each solution to this, the h is the Hessian for the phi, and the s is the gradient for the phi. And then what we're already doing is, yeah, we're gonna. This is the most well-conditioned counterexample for a fixed x bad point and z global min. And this is then the best condition number over all pairs of search rank R and ground truth rank R star. Okay, so we have to move away from arguing from a single counterexample to the entire set of counterexamples. Okay, so here then, this is the condition number, the smallest condition number, the lower bound of that for the engineered point x and the global min z, and then some function alpha and beta, you find a cutting plane for the alpha and beta, and then you optimize over it. And it just so happens that then it proves the statement because this is a lower bound. Okay. So I can talk about this offline, but this is a kind of sketch of the proof. So this is the theorem, right? What it says, let's just see what it says again, is in general, this overparameterization guarantee is false. In order for it to be true, your function actually has to have a bounded condition number. Okay, so your condition number is some kappa, and then this kappa, then this number here is quarter kappa minus 1 squared. This is the number c. This number c. Okay, and what the claim is r star plus c, they're counterexamples, and global min, you can't always guarantee global min, but r plus c times r star. Okay, from that point on, your overparameterization does indeed work. So this is obviously order r star, and if your r star is say equal to 1, then this is order 1. So you're able to actually use overparameterization that's not equal to 1, but it's equal to order 1, and you're able to get global min. Okay, so what does it imply? It implies then if you do gradient descent with order 1 search rank, that's not equal to 1, it's not equal to r star, it's equal to some order r star, but r star is order 1, it's order 1, you're able to get a global linear time guarantee. Okay, so that's the goal. Any questions before I move on? Any questions? Okay. So now I want to talk about the second point, which is, okay, so now you convinced me that you can get the global min. But even if you can get the global min, right, this condition is a bunch of numbers floating around. You need to know the condition number.
Sure, actually,
go.
Maybe very naive. So
yeah.
For low-rank matrix factorization, so is like this P matrix well conditioned because the matrix itself is low rank?
Yeah, that's a great question. I didn't want to spend time to explain, but this holds for the rank restricted version as well. So it's true that in general the condition number is actually infinite, and you need the rank constraint. And actually, the original proof of this is actually for the rank constrained condition number. But trying to explain it was a little bit, so that's why I kind of just said condition number for simplicity. Okay. Yeah. And the other thing is I can always just add a regularizer, and it will be very cheap to add a regularizer. I can actually adjust the condition number. That's a great question. Any other questions? Go ahead.
When you were talking about spurious local minima, I'm curious if your problem satisfies restricted isometry and you use spectral initialization, do you still encounter the same issues of not getting good convergence and failing to converge?
If you use spectral initialization, then you're already in the neighborhood. Yeah. But when does spectral initialization work?
With restricted
and you need A, restricted isometry, and B, you need a ton of samples. Yeah. And maybe you don't have enough samples. And if you have enough samples, your restricted isometry constant is low enough such that you already don't have this problem. Your condition number is already small enough that has no spurious local min, right? But if you don't have enough samples, maybe your condition number is not good. Your delta for your RP holds, but your delta is too high. Maybe RP doesn't hold. And then there, maybe you can use this actually again.
Makes sense.
Okay. Great question. Any other questions? Okay. Now I want to talk about how do you actually certify global optimality. So you say you can get to global optimality, but how do you check that global optimality is actually attained? So it turns out to be very easy. Okay. So in general, it's obviously extremely hard, NP hard, but here in this problem, it's surprisingly simple. When you have this very specific structure of this phi, that's this convex function, and you factor it as fu, which is the phi of u transpose. It's very, very specific structure. It turns out if a point x is rank deficient and is also zero gradient and semi-definite is non-negative curvature, then it's globally optimal. So that's to say, if you give me a local min and I check that it's rank deficient, then the rank deficiency certifies it as being globally optimal. So that's very surprising. When I first saw it, I didn't even believe it. Okay, so let me prove it to you because it's almost too simple to be true. So let me prove it to you. Okay, so the first thing is it's just a convex problem. It's a convex problem. So it has KKT conditions, and the KKT conditions certify global optimality. So what's the KKT? The KKT for this problem is that your solution needs to be semi-definite because there's a constraint here. Okay? So M star is semi-definite, and that the gradient of it needs to also be semi-definite. Okay, and that the product of these two matrices should be equal to 0. Okay, so that's just, if you give me an M and then I verify it's semi-definite, that its gradient is semi-definite, and I can multiply by the gradient and get 0, it already proves it's globally optimal. Okay, and the second step is you discover that this condition gradient is equal to 0. It already implies for the matrix XX transpose, which by the way, obviously is semi-definite. This is obviously semi-definite, but it actually already implies this condition here, okay? Because the gradient, you can just write it out, and the gradient is equal to this, okay? So then your gradient times X transpose already equals this, so it's equal to 0. So of these three conditions, you already have the first condition and the third condition from just this equation right here, okay? So we have not yet needed to use rank deficiency nor the second order condition yet, okay? And the third step is, well, now you need rank deficiency. Okay, now you need rank deficiency. If X is rank deficient, what does it mean? It means there exists a null vector. You can multiply by X and equal to 0. Okay, and that means I form this, you give me any vector Y in Rn, okay, I can compute this with respect to the Hessian, okay? So this matrix Y Z transpose here. Okay, so this thing here, and I just apply it to the Hessian for this F, which this is some raw computation, but what do I see? Okay, I see this term here, let me just ignore this for now, but I see this term here, okay, and I discover that this term has this X times Z Y transpose, and we know X times Z is equal to 0 by hypothesis, so this entire second term is equal to 0, right? And so we conclude that we have actually the second condition because, well, this is non-negative for any choice of Y. Yeah, so therefore XX transpose it satisfies the three conditions. Yeah, so okay, so surprisingly easy. how do you get rank deficiency? You have to overparameterize. If you don't overparameterize, you'll be at the global min, but the only way for you to check is if you're rank deficient. So, okay, you pick a rank that's like 1,000, and then you find it, it's rank deficient, and you're done. But obviously picking 1,000, that's a bit laborious. What I'm suggesting is you drop one at a time, okay? And so this is justified by the next result here, which is this rank lift. So if I just, for some R, I find a second order point. I can use many algorithms to find a second order point, zero gradient, positive significant curvature. And then what I'm doing, I'm gonna add a column of zeros. Okay, I'm gonna add a column of zeros. And that also increases the rank. And well, X plus is trivially rank deficient because I made it rank deficient, yeah? So, okay, if this point still satisfies these two conditions, then it's globally optimal, yeah? And if it doesn't, so it turns out it has to satisfy the first condition, but might not satisfy the second condition, okay? So it might not satisfy the second condition. If it doesn't, then it's a saddle point, and you can use the Hessian to escape, okay? So if you keep doing this, if you keep increasing the rank, you end up with something called the Riemannian staircase, and so you're eventually, hopefully gonna stop, okay? And in practice, it stops, and we actually use this to certify robustness of neural networks, and I might have a little bit of time to talk about it at the very end of this talk. But let's just remind ourselves that global optimality result says at some point R, which is order 1, every second order point is globally optimal. And by that, this has to stop at order 1, yeah? So at some order 1, it finds a global min, increase the rank, but still global min, so then it stops. So this then terminates, and we certify global optimality. So the only trouble is how do we find a rank deficient global min? Okay, so obviously in machine learning community, everyone does gradient descent, and gradient descent is really nice here because it's n by r, so each iteration is as fast as order n, as fast as just n by r, and that's it. Okay. The trouble is that the convergence rate of this turns out, okay, so you have this chi, this chi parameter that's also condition number. That's the condition number of the current iterate. So lambda max of u transpose u, lambda min of u transpose u. Okay. And so what does it mean? It means if your ground truth is well conditioned, then gradient descent is going to converge very, very quickly. If your ground truth is ill-conditioned, it's going to converge slowly, but it's linear convergence, so eventually it's going to get there. What happens if you're rank deficient? Then your R is greater than R star, and your chi has to diverge. Yeah. So actually, if you're converging to a rank deficient point, so if you could get there, then it's certifiably globally optimal. But now you can't get there anymore because your convergence rate is now sublinear. It's exponentially slow. So in this work, what we did was we actually showed if you introduce a preconditioner, okay, if you add this preconditioner here, and okay, you have this weird geometric decay. Let me briefly talk about it in a second, okay? But you can verify this preconditioner is cheap because forming the preconditioner is just this u has very few columns, so u transpose times u is going to be nr squared, and then doing this inverse is going to be r cubed, and then this it's going to take this r by r. It's going to be it's going to be r squared memory, and then applying is going to be nr squared. So okay, it's very cheap, and you just run it. If it's well conditioned, then obviously nothing. It really doesn't matter. But if it's ill conditioned, then it converges like it's well conditioned. Okay, and if it's rank deficient, which is what you want to certify global optimality, it converges. It converges as if it were perfectly conditioned. So now you can actually solve it like gradient descent. Okay. So really the point here is it's completely immune to ill conditioning, but the thing that we care about is that it's also completely immune to rank deficiency. So it seems like a very convoluted setup. And also this geometric decay and this identity perturbation look kind of weird. So actually there was a previous work, and it's also very intuitive. Like if that works, probably this thing works as well, which you just drop this identity perturbation. Why do you have it there? So, okay, so then here, you run this algorithm. It turns out if it's L condition, it also works. There's something called scale GD. So it also works. Okay, but when you're rank deficient, it doesn't work. Okay, you just run it, it just doesn't work. Okay, so I promise you can go ahead and you can try it and it will diverge. It will actually just go, it'll just go away. Okay, so you can come up with algorithms to fix ill conditioning. Okay, the trouble, this is why this thing ends up being so complicated and the proof ended up being 30 pages is rank deficiency. This really being able to handle this rank deficiency is the really difficult part of this this theorem that I'm about to present you here, right? So by adding in this perturbation, allowing to decay geometrically, right? This is the key thing that allows us to actually converge to rank deficient global min, which is then certifiable, and then we can get that. And rank deficiency really, it's not only your iterate is rank deficient, but your preconditioner is also rank deficient, right? Because if your iterate becomes singular, U transpose goes to 0, but yeah, this eta also goes to 0. So then this also becomes singular. And so keeping track of those turns out to be very, very difficult. But if you accept this, then everything I've said so far, you just cut and paste everything together. You use naive classical algorithms to escape saddle points, and then you switch to this algorithm to converge to the global min. And with a large enough search rank over parameterization, you get an end-to-end n log 1 over epsilon guarantee. Yeah, so that's clearly optimal. You can't do Billion order n, or you can't see anything, right? And log 1 over epsilon is linear convergence. Okay. I want to mention here, this inverting singular matrices seems very strange. And you're going to tell me, yeah, you can prove this theorem, but you can't make it work in practice because my experience with singular matrices is if you add a bit of noise, it blows up, right? So we really wanted to show that even with noise, that this algorithm is going to work. Okay, so here what we did was we proved a theorem for the very specific problem, noisy matrix sensing. Some of you are very familiar with this problem here, in which, okay, so my AI satisfy the delta RIP, and then my measurements are normally distributed with a zero mean. So the details are not important, but what we show is that actually this scheme is stable to noise, even though you're inverting a near singular matrix onto noise, you don't blow it up. The convergence is still to a small error. That's actually minimax optimal if you treat this R as order of rank m star. It's actually minimax optimal, even though the iterates become singular, the preconditioner becomes singular as well. And let me just show you that we can actually extend this to SGD in the huge scale. Here we looked at this matrix completion problem here, in which your objective is like this. And when you do SGD, each SGD iteration is just 2 updates on the ith and the jth row of the X matrix here. And you're trying to converge onto the Z matrix that's whose rows are Z1, Z2 to Zn transpose. So each ith row update, right? Every iteration just updates 2 rows, the I and the jth row. And you can of course introduce a preconditioner here, P, right? The preconditioned version of this would just add this P thing here, multiplied by this row. But a cool thing is that you can just pre-compute the preconditioner and you can cache it. And every update then only updates 2 rows of X, so it only updates the preconditioner in a low rank way. So you can just update the preconditioner via the Sherman-Morrison rank 1 update, and then this can be very cheap. So everything can be the same cost as SGD, okay? So you can really hope to solve this on huge scale real world sets with the same complexity as SGD. So let me show you one problem here. So this problem is what we're trying to do is we're trying to denoise the images collected from ultrafast ultrasound imaging, and as you get many frames and the frames look very similar, what you're hoping to do is you're trying to reduce the noise of each frame in aggregate. Obviously a very dumb idea is to just average all the frames together. Can you do a little bit better? So in the literature, in the imaging literature, what they found is what we can do is we can take each frame and we can stack it as the rows of a matrix, and each row is a frame in which we flatten the picture into just a collection of pixels going that way. And so this matrix here, turns out if you factor it, you're going to have a low rank component, and the low rank component is going to be the denoise image, and then the vertical component, if you do a dumb averaging, it'll just be a vector of 1s, but it's going to do better than averaging, and this is going to be denoise component. So our collaborators, our colleagues at UIUC working on imaging, they asked, can you do this with a reduced data rate? So we looked at this, we thought this is just matrix completion, right? What we can do And so we can sample from this matrix here, and then we can compute low rank decomposition, and we can sample it and use SGD to compute this, and then we can do it super, super fast, super reliably. And so here what we're doing is we're just trying to minimize the difference with this sampled pixels, and we add this balancing regularizer to make sure that this non-symmetric, right? It's non-symmetric. So you go in there and you also have to balance, and then we just do Urbana-Champaign on this thing here, right? With the preconditioner with SGD, and we discovered that we're able to denoise this very large image with 60 million pixels. The input looks like this, and the denoise version looks like this. So using other preconditioners, right, the best you can only do is something that looks like this. It blows up the noise because it's a very noisy, you're trying to denoise in the first place, it blows up the noise. If you don't use preconditioning, it doesn't converge at all, okay? We did 30 epochs at 3 minutes on a laptop computer like this one here, okay? And then we're also then able to see what the effects are of downsampling. What we show is actually, you can downsample most of the image, you can keep about 30% of all the pixels in the image, and you're able to denoise the same way as if you had all of the pixels. And the previous techniques required more samples, longer computation. If you use gradient descent, it doesn't converge at all, okay? And really quickly, I just want to show you, so there's been some recent work that said gradient descent with small initialization might converge. So we try to do some experiments. What we discovered is that, so for our data set for this particular problem, it seems like it is the case that small initialization eventually starts working, but it needs many, many iterations at the start when it's trying to converge towards a good direction or something like that. So when we do these experiments, it takes many, many iterations before it starts wanting to converge with the right value of the initialization. And for this problem, my understanding talking to the practitioners is they only want to do 30 iterations because each iteration is extremely expensive, data sets extremely large. Like, just tell me what you can do with 30 iterations. It seems like with only 30 iterations, this technique outperforms gradient descent with small initialization. Let me quickly tell you this optimization problem, neural network verification. Neural networks, we know they can classify pictures of cats as cats, dogs as dogs, but we're scared we make a small perturbation to the picture of a cat and get classified as a dog. Neural networks, basically you put in a picture as X1, and then it goes through this ReLU and then eventually outputs, and it outputs this layer with just 2 elements, and one for cat, one for dog. The element for cat is bigger than the element for dog, then it thinks it's the cat, or vice versa, right? And then if I can perturb the input a little bit and change this to be 0.1, 0.9, then it thinks it's a dog. So you're trying to guarantee that it's going to be robust by proving that you can't do this. So you prove that the gap between cat and dog will always be positive for any small perturbation, okay? And the previous techniques here, the previous people who have approached this problem, right? So you just want to find the lower bounds. They use a linear programming approach to it, but they find that of, say, 100 images, they could attack only 30%, 20% of these. So 70% of them appear to be safe, but they can only guarantee 3% of them are actually being safe, or 4.5% of them as actually being safe. And or 20. So your classifier, it seems to be 77% accurate, but you can only guarantee it's 20% accurate. And then using mixed interpolating techniques, they're able to get it up to, so I can guarantee it's at least 67% accurate, even though it's actually 70% accurate, right? So this is still a bit of a gap. But what we did here is we used Urbana-Champaign, SDP, all of the stuff that we just described, and we used that overparameterization certification, this rank deficiency, right? And then we're able to basically completely close the gap here, okay? And so let me just show you, right? So for example, this digit 1, they're trying to attack it, turn it into a 7. So this neural network thinks it's 99% confident that it's a digit of a 1, but all of these other techniques are not so sure. They're somewhat sure that, okay, it's not going to be attacked. But by the time that this picture here still looks like a 1, we think it looks like a 1. The neural network thinks it looks like a 1, but other techniques, they think maybe that the neural network can be fooled, but we know that the neural network cannot be fooled. And here, the neural network isn't too sure, 55, 43. We can still guarantee the neural network get this right, although only with a small confidence now, but the other techniques completely fail. And here, when they're inverted, right, that's what you expect. So what really we're able to do with this technique, with SDP and with overparameterization, with this certification, they're able to get a much tighter guarantee as you increase the budget for the attacker and they become more and more aggressive. And whereas previous attacks, as they increased the attack budget, then they weren't able to make these guarantees. Okay, so I just want to conclude. Firstly, the core message in this talk is that if you use rank overparameterization, you can overcome the non-convexity of low-rank matrix estimation and optimization, right? Really what we're doing is we're saying that overparameterizing this rank just by order 1, just way less than n, is going to be enough if your problem is well-conditioned. If it's not well-conditioned, then the claim is false. But if it's well-conditioned, then actually that's the key understanding for being able to overparameterize and overcome the ill conditioning. And the argument, novel arguments to trade off the overparameterization with the ill conditioning in order to establish this proof here. And you can just use rank deficiency to certify a local min as globally optimal, but gradient descent doesn't converge. Using a special preconditioner, then it converges to rank deficient, local min, global min, and then it certifies it, okay? And then finally, when we apply this to the real world, we see that it really does work and you solve some interesting problem in communications and signal processing. With that, I thank you for your attention. Thank you very much. Happy to take any questions. Right.
Question from the audience.
Yeah, so in Yuji's work with her scaled gradient descent and preconditioning approach, she also has the plus lambda identity.
Yep.
Same setup for the preconditioning. Can you explain how this approach is different from that work? Absolutely,
and that's a great question here. Yeah. So it's okay. This picture here, okay. So you find that if you add plus lambda, we fix the value of lambda, then I can find you a case in which it diverges. And the reason why is it actually does for overparameterize, okay? So what you actually find is that you can't prove it because it is possible to diverge. Now, the reason why a lot of times it doesn't diverge is actually precisely because this thing here doesn't diverge. Okay, so you can kind of view her scheme as a very special case in which I don't decay eta, but I start the eta being very small.
Oh, I thought there was like a square root of something, right? In her work, like there is some scaling, but it's maybe different from this.
What I understand with Toma from Chicago, right? It's exactly just this with a fixed eta, and chatting with him as well. That's what he told me is the case, right? So it's just fixed eta here, right? And if you fix the eta, it's like the beta being equal to 1. And what they prove is basically so long as this holds roughly true, then it's going to work, right? So if you terminate before this becomes false, then of course then it works. Yeah.
So shrinking
because the eta gets the kappa gets worse and worse. Oh, sorry, this kappa should be chi. Oh wait. No, this is correct. There's a current iterate chi somewhere. Anyway, so there's 2 ways to look at her result. One is that you decay the eta very aggressively, and the other is you hold a constant. And if you hold a constant, then it predicts the first so many iterates will converge, right? And that's also what they see, right? And then if you don't, then eventually it does allow divergence, right? But what they do is they do 2 things. One is they use small initialization, which is a completely different thing to what we're doing here. And 2 is that no, it's really a small initializations that is the other key ingredient. If you use small initialization, it's actually very, very different because you also don't see this picture here. Okay, so you also don't see this picture here for small initialization. What you find with small initialization is that it starts with a long period in which it doesn't make any progress, and it gets linear convergence in all 3 cases. So it's completely different. Okay, so
So there's some work that researchers say that if you start with sport initialization, you have some incremental learning phenomenon.
Yeah. So you don't get this behavior because it's incremental learning. Okay, it's a long discussion, like, but what we're trying to do is we're trying to do local convergence, and local convergence is very different from small initialization. And what the questions we're asking is, how do we solve this problem? The incremental learning is, why does incremental learning happen in the first place? So it's two separate branches of work. Yeah.
So having the shrinkage of beta will accelerate your convergence compared to.
So the beta is actually very subtle. If you shrink it too heavily, then it starts breaking as well.
I see.
Yeah. So there's a range basically for which this eta is in the good range and it doesn't diverge.
I see.
Yeah.
And you have to find that empirically, or is there any?
So we have a theorem, but in practice, my student just hunted for the right value. Sorry. Yes.
Do you know any class of like applied problems, like power generation, say, where the condition number is bounded or is growing at least, no worse than sublinearly? Or is the condition, if the condition number is blowing up by n as the problem is getting bigger, then
yeah. So the condition number is roughly 1 over 1 minus delta. 1 over 1 minus delta for RIP, for example. Now this condition number is, I define the condition number to be just for all ranks. Sorry, let me go find it. Yeah, I should have really defined it. Yeah, I really should have defined it for all n is rank 2r. Wait, so all the perturbations or rank, this is a bit more complicated, right? But so the theorem is proved for the rank restricted version, but it's just, okay, so then M has to be some rank and then the perturbation has to be some rank, etc. So there you can show, for example, Gaussians, right? The condition number is bounded and it gets better and better as you add more samples. For power systems, I'm not 100% sure, but I know that the classic example is matrix sensing Gaussians, and there the condition number for some fixed rank is indeed bounded and improving actually with samples. Yeah.
Can you go back to the matrix completion where you first started at, I think, slide 28? I'm about to teach that in my class.
Okay.
Your version looks different than what I'm about to teach, so I want to understand what your setup is here.
I hope I didn't make a mistake describing this. So.
It's probably different. I think a matrix completion is a matrix with missing data. So in X transpose, where's the missing data here?
Yeah. So what this is actually doing is a little bit different. This is what we call the online learning model, in which what I'm doing is I'm sampling uniformly at random one element at a time.
Oh.
Okay. So at each iteration of SGD, I sample an element. And the claim is actually with order NR log NR, you converge without needing to see all n squared elements, because if you see them, then
different setup.
Yeah.
Thank you.
Yeah. But yeah, absolutely, you can add a sampling parameter here. We're 100% sure we can extend this result, but the proof is going to look similar. There's a lot more technicalities. It's already 30 pages long, so we just haven't done it. Yeah, but we believe you can do a sampling operator here.
On page 24, why does the third, that means the condition number is the worst, why does it converge the fastest?
I'm sorry?
Why?
This one, why does it actually converge faster than this? Yeah, so in fact, I believe it's because that the condition number of yeah, I'm not 100% sure either.
It's a different instance. Different instance.
Yeah, it might be a different instance. I'm not 100% sure. Yeah.
For beta, there was a little.
Yeah. I mean, I got a slide from my students, so I'm gonna go blame them.
Sorry, what is chi here again? That's a different.
That's the condition number. This condition number.
Oh yeah. Of the U transpedition. Okay, thanks. Yeah.
Okay.
Any other questions?
I think that's it.
Yeah. So no questions. That's
okay.
Speaker again.
Thank you.